Hello and welcome to our next lesson, which is continuing with continuities. This is part 2. We looked at graphs last day and trying to figure out where a graph is continuous. And today we're going to be looking at what if we just have the function? What if we don't have a graph? So reminder from your substitution property, you were able to substitute a value from a limit right into a function if it was a polynomial or a rational, as long as that x value that we're approaching is in our domain. And we had some other techniques for being able to simplify and find limits if we couldn't direct substitute. Polynomials we know are continuous everywhere. We know that from graphs of polynomials, there are no holes, there are no discontinuities. So as soon as we have a polynomial, we know that we can say there are no discontinuities, they are continuous everywhere. Rationals we know from experience usually have some sort of non-permissible value. Those result in a discontinuity of either an asymptote or a hole, which again, we know from Math 12 from seeing what those look like. Rationals have asymptotes or holes, and those by definition are discontinuities. The other types of functions we will see is piecewise functions. Piecewise functions can result in a single point that has been removed, which would be a removable discontinuity, or you have multiple pieces where the pieces do not connect and therefore you have jumps. So our job is to take a look at the different types of functions and see where are our discontinuities and why are they discontinuous. Okay? We also will need to remember that the limit must equal the function at the same x value that we are approaching for something to be continuous. So if we take a look at this first question, it's asking us, where are these things discontinuous and why? What type of discontinuity is it? So we had 3 types. We had removable, jump, and infinite. Okay. The first graph we have here is a polynomial. Therefore, it is continuous everywhere. And we know this because our domain is all real numbers. We also know that a cubic looks something like this, right? There's no holes, there's no discontinuities, no asymptotes or anything like that. Okay? The next type of function is a rational. We know that we have a domain of x cannot equal -3. That means that f of -3 is undefined. And the question basically is this undefined like an asymptote or undefined like a hole? So we know from Math 12, we have asymptotes if there are no common factors. If we factor everything and we have a common factor between the numerator and the denominator, then we would have a hole. So the question is, why is it undefined? Is it an asymptote or a hole? We need to factor. Okay. So if I factor this, I get f of x equals x plus 3, x minus 3 over x plus 3. The x plus 3 and x plus 3 cancel out, leaving us with f of x equals x minus 3, which means we have a hole at x equals -3, and that would be discontinuity. What type of discontinuity? That's removable discontinuity. If it had been an asymptote, it would have been infinite discontinuity. The next one is a piecewise. So basically what we're trying to figure out is, are the pieces continuous, but also are the pieces connected at that transition point, or do they jump? Okay. So are the pieces continuous? X squared is continuous. It's a parabola. Okay. We also know x minus 5 is continuous. It's just a straight line. Now, they don't need to be continuous for all real numbers. They just need to be continuous for the domain specified. So if I had something like a square root or whatever, if the domain given to us satisfies the domain of our original restrictions. So what I mean by that is if I had something like x minus 10, we know that x has to be bigger than or equal to 10. We know that's true for a radical. But if it was a piecewise function and they already told us that this piece was only true for x is greater than or equal to 20, then this is continuous. We know that because any number bigger than 20 I plug in will work. Okay. So it doesn't have to be true for every number. It just has to be true for every number in the domain they've given to us there in the piecewise. Okay. So since these are both continuous pieces, basically our job is to figure out, do the two pieces connect at x equals 3? So if I were to draw this graph, for example, when x is less than 3, my function is x minus 5. Looks something like that, and I would have a hole at the end. And our job is to figure out, okay, so for this quadratic portion, is this quadratic portion going to connect like this? Is it going to connect here? Is it going to connect down here? So am I going to jump, or am I going to be connected where I want to be connected there? That's basically what we're trying to figure out. So what I can do is I can just figure out from the left, okay, I'm trying to figure out if these are connected, and therefore I'm really looking to see if my limit exists. So at f of 3 on x squared, we're equal to 3 squared, which is 9. For f of 3 on x minus 5, we're equal to 3 minus 5, which is equal to negative 2. So this means that these are going to have a jump, which means this is discontinuous. And the reason it's discontinuous, if I think about the three criteria, okay, this previous one was discontinuous because f of negative 3 was undefined. This one is discontinuous because the limit as x approaches 3 from the right is of x squared, which is equal to 9, which does not equal the limit as x approaches 3 from the left, because this is on the x minus 5 piece, which is equal to negative 2. So if I think about my three criteria for continuity, this is the criteria that fails. It was the second one in the list from yesterday. This next one is saying, for what values of k will this be continuous? Well, in order for it to be continuous, I need f of 4 to exist. Well, it does, because if I'm on this piece, I have k times 4 squared, which is k times 16. Well, that's going to exist. Okay. I also need the limit as x approaches 4 from the right to equal the limit as x approaches 4 from the left. I need that to be true. So for us, the limit as x approaches 4 from the right is going to be the kx squared section, which will equal to k times 4 squared, or 16k. The limit as x approaches 4 from the left will be 3x minus k, which will equal to 3 times 4 minus k, or 12 minus k. So in order for these to be equal, I would have to have 16k equals 12 minus k, or 17k equals 12, or k is going to have to equal 12 over 17. So the last thing in today's lesson is a theorem. So this is our first theorem. As we go through the different theorems, those of you who are maybe planning on taking an AP exam need to know every theorem we cover. They can ask you about those. They will ask you to use those. Those of you taking Calculus 12 simply as a preview for university, many university profs will ask you to state theorems word for word on midterms or final exams. So knowing these theorems is very important. Most of them basically are saying something very intuitive in a very complicated way. So when we look at this, this is going to make a lot of logical sense. When you read it, it sounds like a bunch of jumbled mess, but when you actually think about what it's saying, it makes sense that it's true. And then it seems a little bit redundant that you're having to use it to show anything, but it's the way it is. Theorems are great fun that way. So the intermediate value theorem says, suppose f is continuous on a closed interval, so from a to b. We're letting n be any number between f of a and f of b. So n is a y value here because f of a is a y value and f of b is a y value. So this is a y value. This is also a y value. Okay, these are x values. Okay, this is a y value. So now we're saying that f of a and f of b are not equal. What we're saying is if this thing is continuous, there has to be some x value c in our interval such that f of c is equal to this y value. Okay. So again, reading it, it sounds like what? I don't even know what that's saying. But if I think about this logically, this makes sense. I'm on a closed interval. These are x values from a to b. Okay. This thing is continuous, this function. Okay. So if it's continuous, it might be doing something like this. It might be doing something like this. Okay. It might be something like this. It could be, well, not, it has to still be a function, so that doesn't actually work. But we might have something like this, right? We could have something like this. Okay? But this thing's continuous. There's no jumps, there's no asymptotes. It's just going along on its merry way. Okay. Okay, so I'm going to draw this guy. All right, so at this point here, this is my one endpoint, and my other endpoint is, I'm just going to actually make this a little bit clearer. Okay, my other endpoint is here. That means this value here is f of a, and this value here is f of b. So this is continuous. So what this means is if I want to start at this y value and work my way up to this b value, I must pass every other y value in the middle, right? And I must do that as I'm continuing along my interval. So if I start at A and I work my way along my curve up to B, I have to at some point hit each one of these y values along the way because there's no way I can all of a sudden just jump to that final y value, f of B. That's what this theorem is saying. As I go along this interval, there has to be some number c in the middle such that this value here is reached. It might be reached multiple times, but it has to be reached at least once. Okay. And every single one, this one also has to be reached once. Every single y value on that left-hand side must be reached at least once as I travel along the interval from A to B. That's all this is saying. Okay? It could be that it exists more than once. The theorem is telling us there has to be at least one. Okay, so something that would be more than once might be something like this. Okay, it doesn't say that f of a has to be smaller than f of b. It doesn't have to be increasing. So for example, if this is my a, this would be my f of a. If, let's say, this is my b, here's my f of b. Okay, so as I travel from A to B, I'm traveling from f of A down to f of B, and I have to hit every y value. So for example, if this is my y value I have to hit here, I've hit it here, 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 maybe here. Okay, so there are actually 4 x values where I reach that desired y value. But I know it has to happen at least once because if it didn't, I would have had to pick my pencil off the page to finish at that f of b value. Okay. So why does this help us? Well, a common question you'll see is questions like this. Use the intermediate value theorem to show that this function has at least one root over this interval. So one root, we know a root happens when y is equal to 0. A root is an x-intercept. So we're trying to show that this will happen at least once. Well, the only way we know that that's going to be true is if this quadratic either starts, if we're over at -7 and at 1, right? This quadratic would either have to start above the axis and end below the axis for us to guarantee that it crosses somewhere, or it would have to start below and end above for us to guarantee that it crosses somewhere, right? And this would cross here, and this would cross here. If that's not true, if it doesn't start above and end below or start below and end above, we cannot guarantee that we have a root without actually finding it. And we don't always have functions that are easy to find the roots. If it starts above and ends above, it could look like this. That does not have a root in that interval. If it starts below and ends below, it could look like this. Again, it doesn't have a root in that interval. So we're basically trying to prove that this must be true by looking at, well, what's my y value at each endpoint? And is this thing continuous? And therefore, must I cross the x-axis somewhere? Okay. So what I need to do is, this would be my a, this would be my b. F of a would be f of -7, which would be -7 squared plus 3 times -7 minus 9. And this gives us 49 minus 21 minus 9. Or this gives us 19. Okay, f of b, therefore we need a negative number here because f of a was positive. And what this means is, this means that on our, this is 1, this is -7, this means we're starting up here somewhere, really high up. So the only way we know we're going to cross the x-axis is if we end up down here. It's the only way we can guarantee this. Right? So f of b would be f of 1. Okay, which would give me 1 squared plus 3 times 1 minus 9, or 1 plus 3 gives me 4 minus 9 gives me -5. Okay, so that means this is ending somewhere down here. So we also know that since this is a quadratic, this is a polynomial, therefore continuous. Okay. According to our theorem, we have to be continuous on our interval. We've got that. And what we're saying is that f of a can't equal f of b. We've got that. And so by definition, we're saying that we must cross my n value, which is the 0 we're looking for, between these two y values here. So we have that -5 is less than n, which is 0, which is less than 19. This is f of b is less than n, is less than f of a. Right? We've shown that this is true. We've got a y value between our two endpoints. Therefore, since we're continuous, by intermediate value theorem, we can just say IVT. There must exist a c in -7 to 1. That would be an x value, c. There's got to be one somewhere in here such that f of c equals 0. Okay, it's got to happen. Otherwise, there's no way you can get from this point to this point, right? There's no way you can get there if you don't cross the axis. It won't happen. And it has to happen because it's continuous. So the only way you could get there without crossing the axis is if you jump over it, which we know doesn't happen because we have a continuous function. Okay? So these all, your write-ups for these will look pretty much identical as you go through. Okay? So this one, this is continuous. It's a polynomial, cubic. Okay? This one again is asking us for a root. They won't all. Some of them might say, show that this has a y value of 5 somewhere in the interval. How do you know? Well, you know because it's continuous and because intermediate value theorem tells us it's true. So does our logic. Our logic also tells us this must be true, but intermediate value theorem is the thing that officially states that this must happen. Okay? So we know it's continuous. F of 1 would be 4 minus 6 plus 3 minus 2, which gives us -1. F of 2 would be 4 times 2 cubed minus 6 times 2 squared plus 3 times 2 minus 2, which gives us 4 times 8, which is 32, minus 6 times 4 plus 6 minus 2, which gives us 12. Okay, so again, we have that f of a does not equal f of b. We've satisfied that. Okay, we have f of a is -1, which is less than 0. It's asking us for a root, which is less than 12, or f of a is less than n is less than f of b. Our n is in between. That's what we need. If it was not in between, we wouldn't be able to show that this is true. Okay, we'd say not possible, cannot be shown, cannot be determined, not enough information, or something along those lines. But this one does. Again, our y value we want is between the y values we have. So by I, B, T, there must exist a C in 1, 2, such that f of C equals 0. Again, if you graph these, what you'll see is that somewhere between 1 and 2, you have this gross x-intercept value. And for the other one, somewhere between -7 and 1, you would have to have, again, an x-intercept. Okay, so you could actually graph these and show that this is true as well, but we're using calculus and this theorem to show. Okay, that is all for today.